Welcome to this explainer. Today we're doing something a little different. We're stepping completely out of the theoretical textbooks and right into the shoes of a senior network architect. Now, assuming you've got your basic Network Plus foundation, you know what a switch is, you know what a router is, we're going to take that and draft a master blueprint for a real enterprise network. We're looking at how to design, implement, and configure Ethernet virtual LANs, exactly how it's done out there in the real-world job market. So grab a coffee, settle in, and let's approach this like real project managers. But first, picture this. It's a typical Monday morning, right? Thousands of employees are logging in, and suddenly a single, faulty network card on one rogue PC somewhere in the building starts flooding the network with malformed broadcast frames. Because the network is just one giant, flat infrastructure, those broadcasts reach literally every single device, switch, and server. The CPUs on all those devices, they just max out trying to process all this junk data. And boom, the entire network grinds to an absolute halt. In the IT industry, we call this a broadcast storm. And let me tell you, if your network isn't properly segmented, this will cause a disastrous outage that can cost your company millions of dollars.
So to make sure you never build a network that falls victim to a broadcast storm, here is our exact project roadmap. First, the broadcast domain problem. Second, enter the virtual LAN. Then, trunking across multiple switches, followed by the 802.1q tagging secret. After that, routing between the VLANs, and finally, real-world VLAN configuration. You'll definitely want to stick around for that last part, because that's the hands-on configuration you'll actually need on the job.
All right, let's dive into part one, the broadcast domain problem and the flaws of flat networks. Before we can build a secure, high-performance architecture, we've got to deeply understand the inherent flaws of a basic, unsegmented network design. A flat network is basically what happens when you just plug a bunch of switches together straight out of the box, without any logical design at all. It forces every single device to process every broadcast frame. That creates massive CPU overhead and huge security risks, mostly because everyone can hear everyone else's traffic. On the flip side, a properly segmented network is the architectural gold standard. By smartly isolating that traffic, we lock down security per department and dramatically improve overall performance.
To really wrap our heads around this abstract concept of broadcast domains, let's picture a physical building. A flat network is kind of like placing your accounting team, your noisy sales floor, and your confidential HR department into one massive echoing warehouse where everyone is just shouting at the exact same time. It's chaotic, it's inefficient, and honestly, zero privacy exists. Virtual LANs or VLANs allow us to build individual soundproof rooms right inside that warehouse.
Now, in reality, that warehouse looks like a standard data center wiring closet. As a junior engineer, you walk in, and the physical cables and server racks just look like one giant intertwined system. All those cables might plug into a single massive switch chassis. But as an architect, you know we actually have to use logic and software to carve that hardware up securely into those soundproofed rooms.
Moving right along to Section 2, enter the virtual LAN and logical segmentation.
So how exactly do we build these soundproof rooms without going out and buying completely separate switches for every single department? Well, the answer is the virtual LAN, or VLAN. By definition, it's a group of devices in the same broadcast domain, but the real magic here is that we're solving a physical problem with a software-level configuration. We're essentially telling the switch, logically, hey, treat ports 1 through 10 as one network and ports 11 through 20 as a completely separate network. The switch itself acts as the barrier. A senior architect demands VLANs in an enterprise network because they drive actual business value. By isolating traffic, we immediately reduce CPU overhead across the board. We can also apply strict security policies, like keeping the guest Wi-Fi traffic completely isolated from the payroll servers, which is absolutely crucial. But most importantly, we limit failure domains. Remember that rogue PC we talked about earlier? If it starts a broadcast storm now, it only affects its specific VLAN. The rest of the company? They just keep working completely unharmed. But here's a thought. It's easy enough to assign different ports on a single switch to different VLANs, right? But in the real world, the accounting department isn't just sitting on one floor. They might be spread across a massive multi-building campus. So how do we connect multiple switches together while maintaining those soundproof walls? That brings us to Section 3, trunking across switches and scaling the enterprise.
To scale our local solution across the entire enterprise campus, we use a concept called trunking. Just imagine if you had to run a separate physical fiber optic cable between buildings for every single VLAN you created. If you have 50 VLANs, you'd literally need 50 cables. That would be an absolute cabling nightmare. VLAN trunking solves this. It creates a single physical link between your switches that multiplexes or supports traffic for as many separate VLANs as you need, all over one single wire.
Which leads perfectly into Section 4, the 802.1q tagging secret, or as I like to call them, digital shipping labels. Running everything over one wire introduces a pretty fascinating technical challenge. If traffic from 50 different departments is traveling across the exact same physical cable, how does the receiving switch know which data belongs to which soundproof room? Well, the answer lies in the IEEE 802.1q standard. Think of it as a digital shipping label. Before a switch sends a frame across the trunk link, it forcefully inserts a 4-byte header right into the Ethernet frame. Embedded in that header is a 12-bit VLAN ID. So when the frame arrives on the other side, the receiving switch reads the shipping label, sees okay, VLAN 20, and forwards it only to the ports assigned to VLAN 20. Now, there's also a really crucial real-world fallback mechanism at play here, and it's called the native VLAN. By default, an 802.1q trunk will actually leave one specific VLAN untagged. It sends those frames without our digital shipping label. We do this to support legacy devices or older switches that simply don't understand modern trunking tags. This ensures that basic connectivity is never entirely lost. So far, we've built a perfectly secure, segmented network. The soundproof rooms are totally impenetrable. But wait, if the isolation is perfect, how does anyone actually communicate with another department? I mean, how does the CEO in the executive VLAN send an email to the HR VLAN? If Layer 2 switching blocks it, we actually have to go one layer higher. Let's look at how we solve that in Section 5, routing between VLANs and Layer 3 communication. To bypass this impenetrable isolation, we have to step up from Layer 2 switching to Layer 3 routing. Because VLANs are technically separate IP subnets, you have to use a router to pass data between them. You basically have 3 architectural options here. Option 1 is using a router with a completely separate physical cable for each VLAN. Pretty clunky and definitely not scalable. Option 2 is what we call router on a stick, which uses one trunked cable and logical sub-interfaces. But option 3 is the modern enterprise standard, using Layer 3 multi-layer switches with SVIs, or switch virtual interfaces. These are insanely powerful switches that have routing capabilities built right into their silicone, processing inter-VLAN traffic at lightning speeds. And finally, we arrive at Section 6, real-world configuration and practical CLI commands. Now that our architectural blueprint is theoretically sound, it's time to transition to the final, practical phase of our project. We need to look strictly at what you, the engineer, will actually be typing at the command line. Reassure yourself right now, this isn't just theory anymore. What we're about to look at are the exact Cisco CLI commands you will use to survive and thrive on day one in the IT job market. Think first, then config. Let's look at how you methodically build an access port. For steps 1 and 2, you create the VLAN and give it a name. You're essentially building the soundproof room and hanging a sign on the door. Then, in step 3, you enter the specific interface configuration. And step 4, the switchport access VLAN command, is where you actually assign that specific door to the room you just built. It's clean, it's logical, and it's highly effective. Next, we configure the trunk connecting our switches together. You select the interface and you issue the switchport mode trunk command. But I really need you to pay attention to step 3 here. As your senior mentor, let me warn you, misconfiguring the allowed VLAN list is a classic rookie mistake. Actually, scratch that, it's a catastrophic mistake. If you accidentally overwrite this list instead of adding to it, you'll sever traffic for other VLANs and cause an immediate network outage. So always double-check your trunk allowances. All right, you now possess the skills to logically segment a network, trunk it across multiple buildings, and route traffic securely between departments. But let me leave you with this final provocative thought. Typing these commands on 1 or 2 switches, pretty easy. But what happens when your enterprise has 500 switches? Are you really going to manually log into every single one? Well, that question leads us right into the fascinating world of network automation and scaling protocols like VTP. But we'll save that blueprint for our next session. Thanks so much for joining this explainer.